transactions are, I can verify them on my own, so I don't need to go through a third party to know that this thing is valid. So I'm not a full node. I'm not downloading the entire blockchain. I'm just downloading the specific transactions that are meant for the addresses or were instigated by the addresses that I own or I'm watching for. You do this through the simplified payment verification part of the protocol. Satoshi actually talked about this in his white paper in I think 2009 or 2008, and it's a good read. Go ahead and look it up in your free time when he talks about SPV especially. So what is SPV? You don't download the entire blockchain. It is very handy for devices that have limited capacity. The one main difference, there are actually a few differences, but the overarching difference between SPV clients and full nodes is instead of get blocks, you're just getting headers of the blocks. So let's see what a block header really is. I'm just going to go ahead and go to the Bitcoin part of it. I guess the network is not doing so well. Right, so imagine blocks without the transaction data. So if I go to chapter 6 of this book, yeah, the network just isn't doing well. And now this isn't doing well. I guess the battery might be dying in that.
Your laptop or anything?
Oh, in the presenting gadget.
Okay, let's try this other one here.
Okay.
If it, let's just.
Yeah, let's go with it.
You use that one.
Okay. Alright, so we can't seem to connect to the network. That's fine. We're going to go ahead with it. Imagine a transaction. Imagine a block without the transaction data, right? So if you have 1,000 transactions coming in to a block, the block size is going to be about roughly anywhere between 500 KB and 1 MB on average. So that's a lot of data for my mobile device to download. If I remove all the transaction data from it, that 1 MB block shrinks down to maybe 1 or 2 kilobytes. And that's definitely data my device can handle, and I can download it. In that block that I download, I am also downloading the in the header that I download, I am also downloading the Merkel route. If you remember from Ryan Charles' presentation, he talked about Merkel routes as summarizing the contents of the block. Right? Does everyone remember that? Yes. Okay, good. If you don't remember that, please look at the end of chapter 7 in Mastering Bitcoin, and we're going to touch on that a little bit right after these couple of slides. Alright, so instead of sending get blocks and getting those 1 MB blocks every time, you are sending get headers and getting 1 or 2 KB headers every time. When you send the get headers message, just like you send the get blocks message, you get a response saying headers, and then headers for about 2,000 blocks. Right? But then I don't really need all the blocks. I just need the blocks that are relevant to the wallet addresses that I have, right? So the scenario is I'm running an SPV client, so I'm running an Android wallet. I don't need to know every single time a block is found or transactions are found on the network. All I need to know is what is relevant to me. The way I would do that is use a filter. So I will say, hey, all of my peers, just give me updates for addresses A, B, and C, and so on. So I'm telling them basically the addresses that exist in my wallet, or the addresses that I'm specifically interested in, and that's a bit of a problem. But we'll get to that in a bit. The way you do this, specify the filter that you want applied to updates that are sent to you. You do that through filter add message and a filter clear message. You can't modify an existing filter. You can just you can't reset stuff, change stuff in the existing filter. So you can't change 0 to 1 bytes. You can clear it and set it all again through the filter add message. You'll know about that in just a little bit when we talk about Bloom filters. So the risk is if I tell all the nodes what addresses I'm interested in, they can discriminate against me, or they can snoop on me, and my privacy is basically lost. And that is not what Bitcoin is supposed to do. I'm not supposed to lose my privacy if I use certain features of the Bitcoin network. The way we guard against that is through the use of Bloom filters. Now, Bloom filters don't actually prevent people from knowing what you are interested in. You just mask it a certain way, so they don't know exactly what you're interested in. There's a probability that they can be certain of what you are interested in, but you can tweak that the privacy and accuracy of the Bloom filter. What is a Bloom filter? Yes.
But is there a limit to the amount of addresses you can add to a filter?
The question is there a limit to the amount of addresses you can add to a filter? No. The filter has a length, and we're just gonna talk about that. So there are two important parts to a Bloom filter. One is the number of hashes, and these are hashes that are known by every other node in the Bitcoin network, or at least the nodes that are competent. So there are hashes that are known by the hash functions that are known by the Bitcoin nodes that you are communicating with, and there's a length of the filter. Now this seems a bit cryptic. I'm just gonna give you the entire filter right now and explain it. So the Bloom filter, when we say a Bloom filter, it is basically a string of zeros and ones right here, right? That is the end result. This is the filter that I give to people. The way we arrive at this filter is, imagine foo is a string. I pass it through two hash functions. So m over here is 2 and n is 10. These are 10 bits, right? I pass foo through the first hash function, and then the result I pass it through the second hash function. The answer that I get would be an integer that I can set to 1 right after I get that response. So for example, if I say foo and pass it through a hash function and it says 2 is the integer that you get back from the hash function, I will change the second bit to 1 if it wasn't already 1. And then I pass it through another hash function, and then it says the fourth integer, the fourth bit, turn it to 1. And then I turn it to 1. And I keep doing this for any of the things that I want to filter information about. So at the end of the day, when you're done with the hash functions, you end up with a sequence of bits that people can compare that data against, and if it matches any turned on bits, which is ones, they know that you are interested in this information. Otherwise, you are not interested in this information. Anything that hashes to the 9th bit over here, I'm interested in it. Anything that hashes to the 10th bit over here, I'm not interested in it. So that's how you communicate what stuff you're interested in without actually revealing the specifics. So my address, they won't actually know what it is. A few mismatches will occur. But they won't know for sure that my address is, what exactly I'm looking for. So you can actually tweak the amount of accuracy in the data you receive and the amount of privacy that you want through varying the number of hashes that you put the data through and the length of the bloom filter. So that will vary the accuracy versus the privacy feature of the bloom filter. So when I say if I'm running an SPV node and I connect to a network, I am giving people this bloom filter, and this is something I arrive at using the addresses that are in my wallet. So I'm basically saying, give me information that is only relevant for these addresses, and these addresses are specified through a bloom filter that you pass to everyone, right? Should be pretty simple. Yes, go ahead.
Yeah, so but once the other node gets the blue filter and goes through all their transactions, right? It checks all the transactions against the blue filter. Wouldn't they then know which addresses are on?
The question is, if they are filtering whatever they send me through a bloom filter, wouldn't they know exactly what I'm interested in? No, they won't, because there will be some false positives.
Yeah, but you'll know that the addresses are within a subset.
Yeah.
Right.
So the comment is, but it's the addresses are a subset of this. Yes, this is why you are able to vary the M and N to add some dilution to it. So you can. It's not perfect, but it's something better than saying these are exactly my addresses, right? I think you'll be happy with it once you start using it, unless people come after you and you didn't do it right. Yes, go ahead.
So in your example, foo and bar are the addresses?
The question is the foo and bar and in those in the bloom filter example addresses. Yes, they are addresses. All right, so I have connected to a node, and it's sending me updates about these addresses that I asked it for. And what am I supposed to do? Just take his word for it? I'm connected to one node, and he's sending me updates on this that no one else is sending. What do I do with this guy? How do I believe whatever he is saying? The way you do that is, it's in the name, Simple Payment Verification Protocol, right? SPV. So there needs to be a way that you can independently verify that the data he is sending you, or she is sending you, is actually valid. So for example, if they say, yeah, the transaction you sent, it was confirmed in this block. I can't just take its word for it. I need to use a way to verify that information. The way I do that is through Merkel Routes and Merkel paths. If you remember Merkel Routes, they were basically, you can summarize the entire block, the contents of the block, in a hash string that is 32 bytes, right? So the way you do that is, in this binary graph, in the binary tree, you have all the transactions as leaf nodes, right? You take these two, get the hash for transaction 2, get the hash for transaction 3, combine that, take a hash of that, combine that with the other hash in that level, combine that, take a hash of that, and then you end up with a 32-byte summary of the entire block. Now, what is that's a Merkel route, and you talked about that last week. You can use this to verify what transaction, if a transaction is actually a part of this. The way you do that is you need to be specified a path to this verification, and that is called a Merkel path. What is a Merkel path? So for example, imagine I have an address A, and it received some coins in transaction 2. So this is the transaction I'm interested in. Now, when the node sends me an update, and they say transaction 2 was verified by this block, they are going to send you the hash for the transaction 2, the hash for the transaction 3, so I can hash these and arrive here. They're also going to give me the hash to this, right? This value. So I can combine all of these values and arrive at a root hash that is the Merkel route that is passed in the block header. Does that make sense? So I'm getting a path to verification whether this transaction is actually a part of the block. Now, the guy can come up with a block's Merkel route that is basically lying to you. It's all made up. This is why you need to connect to more than one node and hope to come across an honest node, right? So, yes, go ahead.
Sounds like the transactions needs to be ordered. How are they ordered by?
The question is, the transactions need to be ordered. How are they ordered? This is one of the things we can randomize. So when we mine blocks, we can randomize the nodes that is hashed, and we can also randomize the order of the transactions. That also changes the hash. Okay, so this can be any order.
But if I have a block and with a set of transactions, if I want to come up with the root hash to match to whoever solved the problem, don't I need to know the order so I can complete this hash and go up the tree?
The question is, don't I need to know the order of all the transactions in this binary tree to be able to come up with the Merkel root hash? You don't need all of the leaves. You just need approximately log n to the base 2 data. And the way you do that is, you want data for this transaction 2. You are also provided with the hash for transaction 3, so you can combine this and come up with this one, right? And then you are not provided with this data. This is not what you're provided. You're provided with this, okay? And you can combine this and come up with the root hash. Okay, so the complexity is not linearly increasing. It's log base 2 increasing, right? So it's a lot better than what you would have if you were to download a 1 MB block, right? Because the difficulty doesn't increase linearly, or the data doesn't increase linearly. Does that make sense? All right, so that's what a Merkel path is. You in SPV, you use Merkel paths very heavily to verify the data that you receive. All right, so we talked about one caveat and the second one as well. So there's loss of privacy and security. When you are using SPV, you are also hoping to come across a node that is honest and is not lying to you. And for this reason, you need to connect to more than one node, and preferably in different locales and so on. At the end of the day, if you want complete privacy and complete security, I shouldn't say complete privacy. If you want privacy and security, your best bet is to use a full node. Don't go through a third-party service. If this is exactly what you're looking for and you have the chops to do this technically, you need to run a full node. That is the cost of your security and privacy, right? All right, let's talk about unconfirmed transactions. So we talked about the blockchain. We can download the blockchain, but the blockchain is basically confirmed transactions and blocks and so on. What happens if I receive an unconfirmed transaction through an inventory message? You store it in a memory. Let's call it the main pool. You can call it whatever you want. Let's store it in memory. You can write it on disk if you want. If this transaction is not confirmed after some time, I don't need to carry it because this transaction was bogus. So this will happen if you're sending a transaction on the Bitcoin network. with 0 fees, and that transaction is like, uh, 50 or 60 kilobytes. Miners may not want to mine that transaction. Sometimes they do, but most of the time they will not want to mine that transaction. So the typical timeout on the Bitcoin Core is about a week for this transaction to be removed from the memory pool, right? And that's arbitrary. You can change it the way you want it to be. When you receive a transaction and it's unconfirmed, you need to link it to the transaction's parents. Who are the transaction's parents? Every transaction is spending outputs from another transaction, right? What if you get this transaction and it is spending outputs from a transaction that you don't know about? Well, to you, this seems like an orphan transaction. It's just on its own. There's nothing linking to it, or it's not linking to anything valid. Then you put it in an orphan pool. So there's the main pool, and then there's the orphan pool. When in the future you do receive the transaction whose outputs were being spent, which is the parent transaction, you can remove this transaction from the orphan pool, and you can put it back in the main pool where it belongs. Right, and you can do this recursively through the orphan pool. So all the transactions that came after it, or all the transactions that are affected by the new transaction that you just received, are removed from the orphan pool as well. Right, pretty simple. And then in the future, a block will probably mine one of these transactions or most of these transactions, and you will remove them from the main pool, and you will write them on disk into your version of the blockchain, right? And you will tell other people about it, and so on. All right, so this is all very interesting. But why do you need to know this? You need to know this because you can come up with some pretty nifty ideas that you can use the Bitcoin network for. One of them is, I really hope the internet is working now. One of them is coinometrics. It's working, yes.
Am I trying a couple of three?
Sorry? 3?
Yeah, number 3.
I don't think I have the password for that.
I'll get it right here.
Okay. All right. So Coinometrics is an analytics site, and there are a few of these out there. You can go here and you can look at some pretty cool. I guess not.